Good evening, everyone. Welcome to the live session. Today, we'll be discussing practice problems from week 4's content. So, for a brief introduction, I am Poulumi. I'm one of the TAs for the NPTEL Natural Language Processing course. Like every time, we'll wait for 5 minutes for everybody to join in, and we'll start at 7:05. Okay, all right, everyone. Let's get started with today's live session. So the first problem for today is this one. So we have to answer that bomb wedge algorithm, which was discussed in the video lectures. It is an example of which of the following: forward backward algorithm, expectation maximization, or which of the either options. So please try solving this problem. We'll take 1 minute time, and then we'll discuss the solution. So please try solving this problem once. Yes, Sita Lakshmi, you have raised your hand. Do you have any doubt? Okay.
No, ma'am. Oh, no, no, ma'am. I don't have any doubt, ma'am.
You wanted to answer the question, is it?
See, ma'am.
Okay, okay.
Both, ma'am. Forward, backward algorithm and the special case.
Okay, okay. Okay, let's discuss this problem. Um, so let's see. Three of you have answered this question, and all of you think that the answer should be C. So, which should be an instance of forward backward algorithm and expectation maximization. So let's take it up one by one. So why should Bombwell should be an special case of expectation maximization algorithm? Could anybody answer? Like let's take Sita Lakshmi. You had answered C, right? So you think that Bombwitch is an example, is a special case of expectation maximization algorithm. So why is it the case? Mm, okay. Okay, then let's ask SS Barpe. You also think the answer is both A and B, right? So why do you think that? Why do you think that that is the case? Could you please explain? I hope I'm audible today, right? Could anybody just confirm? Am I audible? Okay, okay. Okay, fine. Maybe we can. Okay, maybe we can directly jump onto the solution then. So, um, the solution is indeed C. Now we need to just briefly explain that why that is the case. So, what makes Baum-Wilch algorithm a special case of expectation maximization algorithm? Would anybody like to say? Otherwise, we'll discuss anyways. Anybody can unmute yourself and say. Uh, Okay. So what do we do in Baum-Welch algorithm is that we find the parameters of the hidden Markov model, right? And when do we do that? When we do that when a label corpus is not available to us. So if a label corpus was available, where each of the words would have been labeled with the corresponding part of speech tags, then we could just take the MLE estimate for each of the, say, the transition probability, emission probability. Those would be simply the MLE estimates in this case. However, when a labeled corpus is not available, all we have is a corpus unlabeled. So it would not, so it would simply be a sequence of words and nothing more than that. We don't have any tags or any idea about that. So in that case, how do we solve the HMM pure tagging problem? So in that case also we need to estimate all the probabilities, all the transition probability matrix, emission probability matrix, initial probabilities. In that case, we use Baum-Welch algorithm. And what it does is, what expectation maximization algorithm comes over here is, so given the observation, given the corpus, I need to estimate the unknown parameters over here in such a way that it maximizes the likelihood of the observation, which is the corpus in this case. So that is why Baum-Welch algorithm is a special case of expectation maximization algorithm. Um, and why do we need backward forward algorithm over here in Baum-Welch algorithm? Anybody would like to comment? So here, backward forward algorithm is used. So in the video lectures we saw that Baum-Welch algorithm is, yes. Somebody has
Ma'am,
me. Yeah.
we try to focus what has happened already, and we try to predict what next also. Therefore, it is forward backward. That is what I think.
Oh, okay. It's slightly different. So the thing is that uh, in backward forward algorithm is we need to compute the state probabilities. So in order to compute the state probabilities, we first go from the start of the sequence to the end of the sequence in the forward direction, and we keep on calculating probabilities. So that is the forward algorithm. Whereas there's a second part where we start from the end of the sequence and try coming to the start of the sequence in a backward fashion to compute backward probabilities. So both of them, so both forward and backward probabilities are computed, and that allows us to efficiently solve the Baum-Welch algorithm. So that is why it is the forward backward algorithm. And so in Baum-Welch, we know that we iteratively follow. Just a second. So we iteratively follow a process. So where we initially start with some randomized probability values, and then based on that we make some estimates, and we uh, keep on updating those estimates unless and until we reach a convergence. Okay, so all these are different elements in the Baum-Welch algorithm, and that is why I mean here in when we are estimating the state probabilities, the state sequence probabilities, here we require a backward forward algorithm. Okay. So because of that, the answer for the first question would be C, both A and B. Does anybody have any doubt in this question? Okay. Okay, then we'll go on to the next question. So over here, we are given the state transition probabilities in a couple of states. We need to, so given that the weather on a particular day is sunny, we need to calculate this probability. So there's a numerical problem. Please take a few minutes and try solving the problem. And if you can, just once you're done solving, please post your answers in the chat, and we'll take up the solution in a couple of minutes. So nobody has yet posted the solution. Are you guys stuck at any point that you want me to explain the problem once? Or is there any doubt? So you can unmute yourselves and ask, or you can post in the chat as well. Okay, so Mukta has given the answer. Okay, and SS Bharti also. Um, Others also please join in. So there are 27 people in the chat in the live session today. Everybody please try once.
Hello, madam.
Yes.
Uh, for previous question, I could not give the answer.
Yeah.
Can I give the answer now? Because
Yes.
I was busy with something, that's why I could not give the answer.
No
Uh,
problem. So yes, go on.
Madam, in this question, the state transition probabilities are given in the form of table. So for a rainy state, there is a state one. For cloudy state two, and for sunny state three is given. Right. Um, Here, the first initial state is a sunny, and the transition given is given in the question, that is sunny, sunny, rainy, rainy, sunny, cloudy, sunny. And from this table, we can take the value for uh, from S3 to S3. The value is zero point 0.8. Then from S3 to S3, that is sunny to sunny, again value is zero point 0.8. From sunny to rain, the value is zero point 0.1. In this way, I have multiplied these values, and then I got the result 1.536 into 10 raised to minus 4.
Okay. Okay. I think you have followed the correct approach only. It's correct.
Thank you, ma'am.
Would anybody else like to join in and like to add on to what she said? Okay. We'll go on to discussing the solution then. Uh, so it's just would be an reiteration of what she said, but still I'll go over to the solution and so that everybody can understand once. So we are given three states over here. So state one is rainy, state two is cloudy, and state three is sunny. And we have been given certain pointers. So we are given that whether on the first day, that is t is equals to 1, is sunny, and so from here, what can we conclude? That from here we get the initial probabilities, initial state probabilities of each of the three states that we have. So we have three states, S1, S2, S3, and it is given for sure that on the first day it's sunny. So probability of S3 given start would be 1, whereas the starting probability for the rest of the other states, that is S1 and S2, it would be 0. Now this is given in our sequence. This would be the final the state sequence for which we need to compute the probability. Okay, and so here we can see that from the transition probabilities that are given to us, we can also draw the corresponding state graph. So here we have three states that we can observe. So we have C for cloudy, R for rainy, S for sunny, and let's take some values. So S1 to S2 is 0 0.3, so we can see the corresponding tags over here, and we see that the probabilities are marked on the tags, and this can give us a good way to visualize the transition probabilities that are given to us. So how do we compute the probability? So here we simply take the sequence and we break it down in terms of the probability. So it would be probability of S3 given start. So we are starting on the first day it is sunny. So we are starting with S3 state. So this is the initial state probability. This is where it comes. So the statement that was given over here, right? That given that the weather on day one is sunny, so this is where we are using the fact. So probability of S3 given start would be 1. Then after that we simply have the various transition probabilities. So probability of S3 given S3 is again like we take pairs. So again S3 given S3, S3 given S1, and we go on like this. And finally we compute all the probabilities, we multiply them, and we get finally this value. So I hope this is clear to everyone. Does anybody have any doubt?
Ma'am, actually,
Yes.
can you explain the fourth step, ma'am? How do we got that A33, A33, A31?
Oh, okay. So this A33 just means this is the transition probability of going from state 3 to state 3. Whereas A31 means this is the transition probability of going from state 3 to state 1. Okay. So so if I take A31, what is A31? Probability of going, so A31 you can find over here. Wait a second. So sorry, just a second. So A31 is this one, right? Probability of S1 given S3. So going from S3 to S1. So we see S1, S3 to S1 is 0.1. Okay, so this gives you the value.
S3 and S1 we have to see, ma'am.
Yes, yes. So A31 means that I'm transitioning from state 3 to state 1. Okay.
Okay, S3 is state 3.
S3 state 3. S3 to S1, this is the corresponding. I hope you can see the cursor. S3 to S1 we are going. So this is the corresponding cell that gives me the transition probability, 0.1. We can take another one, say A23, right? What does A23 mean? It is the probability, the transition probability of going from state 2 to state 3. Okay. So what would be the
How
value?
do we get that? In third step, we see that P of S3, S2.
Hmm.
But
So I'm
we have
simply
taken
writing this notation. These are the same. These are, you can ignore this. Till here, did you understand? Till step 2, did you understand where I've written it in terms of probabilities? I'm just using.
So in first step we have S3.
Hmm.
So that is the start and S3 and then again you have given S3. So there I got confusion.
Here, you're saying where
Okay, that is the previous first starting the S3 and then the S3 of that is the previous one and the current one is also S3.
So there are three S3s in the beginning, right? So first we need to take into account that what is the probability of starting with S3. Okay, you can implicitly assume there's a start before this, which I have not written. If that was there, then this would be clear, right? So it would be like probability that I'm starting from S3. So S3 given start, then S3 given S3, again S3 given S3, then S1 given S3, S1 given S1, S3 given S1, S2 given S3, and finally S3 given S2.
Yes, got it. So ma'am, here that make any doesn't make any difference, no? Whether we write S3 first or S2 first.
Here, this one.
Yeah, in fourth step, ma'am, because A33 you have given, so that is the first, second step we have P of S3, S3.
Hmm.
So, and then you have to
Okay,
write
you can forget about this. Forget about this step. This A, where this A's are written, forget about that. So let's take it up from here. Let's take it up from this step. Okay, the second step. So what would be probability of S3 given start? We computed in the last slide. It is 1. Okay.
one.
Okay. Now let's take this probability of S3 given S3. It means what is the probability that I'm transitioning from state 3 to state 3? So here, this loop, right? This loop.
Yeah.
This loop or this value. Okay.
Yeah.
Next is again the same thing is there, so it would be again 0.8. Then we have probability of S1 given S3. Okay. So I'm transitioning
0.3.
0.1. So I'm
Okay.
transitioning from S1 to S3.
S1 to S3.
So where is S1 is rainy, right? From rainy to sunny, I'm going.
Okay.
Huh. So like that.
Ma'am, that first we have to consider S3 or previous one, ma'am, to see that states actually.
Hmm.
For example,
Huh.
in okay, you will take A31. Okay, that is the P of S1, S3. So whether we have to first see the S1 or S3, we have to see the state.
So it would be S3. S3 I need to
Okay, we
see.
have to see the previous state and then we have to go to the current state.
Yeah.
Okay, okay, ma'am.
So
So
you
we
can
have to
see
go
over
to
here. So you can see this row,
yeah,
right? S.
S2 and then S1.
Hmm.
So
So that,
that will be 0.1.
yeah, yeah.
Okay, okay. Got it, ma'am.
Okay. Anybody has
Thank you,
any?
ma'am.
Yeah. Anybody has any other doubt? Okay. We'll go on to the next problem. So this is also a similar problem. So here we are given a sequence and possible pure stars. We need to compute the probability of this. So we have states and observations over here. We have to compute the joint probability. We'll wait again for like 1 or 2 minutes. Just please try once. Okay, we'll discuss the solution. So we'll start by checking what are the. So, in order to solve this problem, we need to first check what are the different values for the initial probabilities, transition, and emission probabilities that are given to us. So, we are readily given the tables for emission and transition probabilities, whereas for initial probabilities, we have been given the statement that all the pure stacks are equally likely to be at the starting of a sequence, and the possible pure stacks are T1, T2, T3 and T4. So the starting probability would be equally distributed among all these stats. So the probability of T1 given start, T2 given start, T3 given start, and T4 given start would be 1 by 4. Now this is what we have been asked. So probability of x1 is equals to key, x2 is equals to fin, y1 equals to t1, and y2 equals to t3. So what would this mean? So this is like first we need to start at the t1 state. Now once I'm at the t1 state, so that is probability of t1 given start. Now once I'm at the t1 state, this state would emit the tag key. So that is why we have the emission probability of key given t1. Then again we transition from T1 to T2, that is probability of T2 given T1, that is the transition probability. And finally, once I am at T2, I emit the word fin. So here we again have the emission probability of fin given T2. So we are taking the product of the start probability of P1 given start. We have emission probabilities as well and a transition probability. Then we simply plug in the values and we get this to be the answer. Does anybody have any doubt in this problem? I hope everybody is able to solve the problem. I didn't see many people post their answers in the chat. So yes, somebody is unmuted. Okay. So have everybody understood this problem? Were you also able to solve this problem? Any doubt over here?
Ma'am, can you please repeat third last step?
Third last step. Okay. Here, this one you're saying?
Yes, ma'am.
Okay. So we have been asked to compute the joint probability of certain states and certain observations. So what are the states over here? States are the tags T1 and T2. Okay. And we have to, and these are the observations, the word key and fin. Okay. So how do we compute the probability? We can look at this figure once. So first we start with the tag T1. So for that, for starting with the tag T1, we need to take into account the initial probability of tag T1. So that is why we have probability of T1 given start. Okay. Then what do we do? Once we are at the tag, once we are at the state T1, T1 emits the word key. So that is why we have the emission probability of key given T1. Next, we transition from T1 to T2. So for that, we have the transition probability of T2 given T1. And finally, once we are at the state T2, so T2 emits the word fin. Okay. So probability of fin given T2. So remember this is an HMM based technique, right? In HMM based technique, what do we do here? The hidden states, that is the tags, they are expected to emit the observations. So that is why we have this observation probabilities and emission probabilities over here. Whereas in the previous problem, in this problem, we didn't have all these things. We simply had a product of different transition probabilities. Because in this is a simple Markov model, simple Markov chain. Here we simply have states. States and observations are the same. Okay, here there's no specific distinction. Whereas in this problem there is a distinction. We have states which are hidden. We have observations which are the words. And because of that, we have this emission probabilities and transition probabilities. And finally, like we can plug in the values. So probability of T1 given start, we compute it over here. It's 1 by 4. What is probability of key given T1? We can check over here. So what is the probability that tag T1 emitted key is 0.1, fin is 0.1, and NE is 0.8. The value for R that we are concerned about is this one, 0.1. Okay. and then probability of T2 given T1. So we're transitioning from T1 to T2. So the value is this 0.01. Okay, this gives us the transition probability. Finally, probability of fin given T2 is here. So we go to tag T2 and we observe what is the probability with which it can emit the word fin. It's 0.1. So these are how we get the values from the tables, and then we simply take a product and we arrive at the final answer.
Ma'am, actually one doubt.
Yes.
How do we get that actually P of given stack? We got 0.25 now, ma'am.
Yes.
How do we got that, ma'am?
Okay. So in the problem, it is given that we have to assume all the tags are equally likely to be at the starting of the sequence. Okay. So this is mentioned. And now what are the number of tags that are given to us? We have four possible tags, T1, T2, 3T, 3, 4. So the starting probability needs to be distributed uniformly among all these tags. So that is why each of the tags, whether it's be T1 given start, T2 given start, T3 given start, or T4, they have been assigned an equal probability of 1 by 4. So that is 0.25.
Okay, ma'am, got it.
Okay. So prior to this, somebody had asked me to explain again. Is it clear now?
Yes, ma'am.
Okay. Any other doubt? I hope it is clear how we are arriving at this step, right? So this is the most crucial step. After that, we simply need to plug in the values. I hope this step is clear. Okay. I hope there are no more doubts. Let's go on to the next problem. So here what we are asked is, here we need to give the size of the state transition matrix, emission matrix, and we have been given certain data, some information is given to us based on that. This is a sort of a intuitive problem. I expect everybody to try and post their answers in the chat. We'll wait for 1 minute. So only one of you have answered this question. Are you all stuck at any point? Okay. Then maybe we can we'll directly jump over to the solution then. Okay. Um, so the solution is A in this case. Why is that the case? We are given two things. So we are given that there are k hidden states that are available. So what would be the state transition matrix? What do we see in state transition matrix? It is like we have k hidden states, and from each hidden state I'm transitioning to every other hidden state. Okay, so that is what the state transition matrix, uh, that is what are the values it holds. So because of that I have k cross k. And what about the emission matrix? Emission matrix is like we have k hidden state, and at each hidden state I can emit t possible things. Okay, t possible observations are there. Because of that, the emission matrix would have a size of k cos 3, k cos t. Sorry. Um, so because of that, the answer is A. Is this clear to everyone, or does anybody have a doubt?
Yes, ma'am. Clear.
Clear. Okay. Okay. Um, okay. Then we'll jump on to the next question. So this is the question. So this is a problem based on the maximum entropy model. So just try solving the problem once. We'll follow the same process. We'll wait for a couple of minutes. I hope you all will try, and then we'll discuss the solution. So are you all trying the problem? Should we wait for a few more minutes, or we can jump on a solution as well? Or I was hoping if you all could also try. So are you all trying? In that case, we can wait for a few more minutes. Okay, okay. Okay, I think we can now discuss the solution. Let's see, two of you have answered. Chandra Kala and Samyukta Hedke. Would you like to add your thoughts on how did you solve the problem? Both of you have said the answer is C, right? So let's hear from one of you. Samyukta, would you like to say?
Yeah, I actually used the entropy formula for that.
Okay.
So you consider the number of the vocabulary size is 1,000, and out of that, the number of stop words is 100. So the probability of each has a probability of 0.0019. So I calculated that the probability of the other words that might appear would be 1, 1 minus 0.81,
Okay.
and and then the remaining words, the count of the remaining words is actually 800 because the 100, sorry, 900, sorry.
Yeah.
The count of the remaining words is 900, and I added that px log to the base 2 px, the formula I used for each of this.
Okay. Okay. And with that, you got C. Okay.
Yeah.
I think you're thinking the right way. Okay. Um, and Chandra Kala, would you like to add something to this? Add something to what she said? Okay. Okay. We'll discuss the solution then. So the answer is C. So here the main idea that we need to use is, so it's given in the problem that we have to solve the problem based on the maximum entropy idea. So what is the main idea in the maximum entropy, in the maximum entropy model? Just that, so we have to model all that is known and assume nothing beyond what is unknown. So given a collection of facts, we need to choose a model which is consistent with those facts, and otherwise it should be as uniform as possible. So this is very important, that it should be as uniform as possible for the other things that is beyond the given facts. Okay. So here in the problem it is given that we have 100 stop words, each occurring with a probability of 0.009. So what is the overall probability of all the stop words? 100 into 0.0019. So 100 is the number of stop words, and this 0.001 is individual probability of each of the stop words. So that gives us 0.19. Okay. So in my corpus, I have both stop words and non-stop words. So based on the value that we just computed, what will be the probability of non-stop words? It would be 1 minus 0.19. So this is 0.81. However, this is the overall probability of all the words which are non-stop words. And here what comes in is, for maximum entropy, this remaining probability with the 0.81, it should be uniformly distributed. So for every non-stop word W, so we first need to count what are the number of non-stop words. So it is 1000 minus 100, which is 900. So the 0.81 needs to be uniformly distributed among this 900 non-stop words. That gives us a value of 0.0009 for each of the non-stop word. Now finally, we need to compute the value of entropy. For that, we use the formula. So according to the formula, so first we have 100. 100 is the number of stop words. And into that, we need to take into account the probability. So it's p log 1 by p, or minus of p log p. So here we have p, which is the probability of each of the stop words, and log of that, and the minus sign before it. So this is the entropy term that is coming due to the stop words. And here this is the entropy term due to the non-stop words. So first we have the number of non-stop words, which is 900. Then the probability of each non-stop word. So p over in this term is 0.0009, and log of p again, and a minus sign before that. So this is the overall probability that I get, and the final value is minus 2.98. So the correct answer is C. Um, does anybody have any doubt in this problem?
Madam,
Yes.
could you please explain that sentence for every non-stop word?
This one? Yes, yes. So what happens in maximum entropy? Maximum entropy, the main idea is that, look, just read the sentence one. So, sorry. So, given a collection of facts, we need to choose a model which is consistent with those facts, but otherwise as uniform as possible. So, what is the fact that is given to us? In our problem, the only fact, the only constraint that is given to us, we are given a constraint on the probability of stop words. It is given that out of 1,000 words, we know that there are 100 words which are stop words and each has a probability of 0.0019. So this is the empirical fact that we have obtained from our data. Okay. But nothing is mentioned about non-stop words. So that is where we need to be as uniform as possible. Okay. So first we get started. Till here, I think you have understood. So till here we first compute the probability of stop words, then the probability of all the stop words, all the non-stop words that are there in the corpus, which is 0.881. Now we need to distribute this probability uniformly among all the non-stoppers that are there in the corpus. We need a count for that. What are the number of non-stoppers? Is 100 minus 1,000. So it is given total there are 100 words, among which 1,000 words. Total there are 1,000 words, among which there are 100 stop words. So the number of non-stop words would be 900. We simply divide the probability 0.81 by 900 and that gives us a value of 0.0009. This is for every non-stop word. Is it clear now?
Madam, it means it is the
Yes.
probability of each non-stop word, right?
Correct, correct. Any other doubt?
Ma'am, last x is equal to e of log of 1 by 3, no ma'am?
Yes.
But here the values are given different, minus 100.
This is the formula. This is just the expression. I've expanded the formula. So the formula is for each term, I need to take into account first the number of occurrences, then p log 1 by p, or minus of minus of p log p. So that is how it is expanding. So say in this term, the first term if you see, so this accounts for the stop words. So how many stop words are there? There are 100, right? Then what is the probability of each stop word? Is 0.0019, right? So we have p, and this is log 1 by p, which you can also write as minus log p. So that is what this is.
Okay, okay.
Is it clear now?
Yes.
Okay. Okay, I hope everybody has been able to understand this problem. Um, we'll go on to the next question then, in case nobody has any other doubt. Does anybody have any other doubt? I hope nobody is saying anything.
No, ma'am.
No, right? Okay, okay, fine. Okay, I'll go on to the next problem. Okay. So here again, we need to find the dimensions of the parameter matrices in a HMM model. And what we are given is the number of hidden states and the number of observable states. So we can discuss this problem. So this is actually similar to one of the problems that we did today. So I was hoping if one of you can explain it this time. Let's see. How about Lokesh? Lokesh have said the answer is B. Would you like to explain?
Yeah, actually that asked for the three things. One is the transition matrix. Since we have n hidden states, it will be n plus n.
Hmm.
And emission matrix with v observable states, so it is n plus v.
Hmm.
And then the probability matrix, so with the start. So that will be n. We have n variable, n hidden states, and the start state will be one. So it is n minus one.
Okay. Okay. Correct. Would anybody else also like to add something? All right. So it's correct. I think all of you who attempted it and posted your answer in the chat have got it correct. So what we are given over here is we have n hidden states, v observable states. So what we do in transition matrix, we have transition probabilities. Transition probabilities take into account the fact that we are transitioning from one state to another. So for each of the n hidden states, I'm transitioning to every other hidden state. So that gives us n cross n. Whereas for emission probabilities, so emission probability comes into place where we have a tag, and each tag or each of the hidden states is emitting one of the observable states. Okay, so for one hidden state there are v possible options. For n hidden states, it would be n cross v, like that. And finally, for the initial probability matrix, there are n hidden states, and for each hidden state, what is the probability? Say for the ith hidden state, what is the probability that it is the tag or the hidden state from which we start our HMM model? That would be contained in the initial probability matrix. So that is n cross 1. Is this clear to everyone?
Yes, ma'am, clear.
Okay. So let's try the seventh problem now. So here we are given an input sentence. That note is a great enemy, and we are given the possible tags for each of the words that are there in the input sentence. And now we need to say what are the number of hidden state sequences possible. So please just try solving the problem once, and we'll wait for 1 minute. Okay, so some of you have attempted the question. Um, let's see. Suvarna Bhagwat, have mentioned that the answer is A. Would you like to explain how you came to this solution?
Ma'am, there are four possible tags for the first word, three
Hmm.
possible tags for the second,
Hmm.
and then third, fourth, and fifth word, they respectively have only one possible tag.
Hmm.
And again, the last word has three possible tags. So for the words which are having one possible tag, if we multiply the all possible combinations of this, so they will come up as 4 into 3.
Correct, correct. That's correct. Um, all right. As she said, so we have so for each possible hidden state sequence, we need to take into account for each of the words how many possibilities are there, how many pure tags are possible. So and after that, we simply take a product of the number of candidates for each word. Okay. So which gives us 4 into 3 into 1 into 1 into 3, which are the number of possibilities for each of the word. Okay. So this is how we get the answer. Um, did everybody understand this problem? Anybody has any doubt? Okay, okay. I hope you all have understood. Let's. If somebody has unmuted.
And is that simple to know that keywords tagging labels are to used NN and NNP, NNS, NNB?
Mm-hmm. I didn't get your question. Could you please repeat once?
Yeah, this keywords tagging is used as a notation, right? NN,
Mm-hmm.
NNS,
Yes, yes. So the
because I cannot go through the sessions yet.
okay, okay. So yeah, so these are the pure tags from the UPenn tree bank. So what does it mean? So for example, ADT means A is the word and DT means it's a determiner. Whereas is VB, it means it's verb in base form like that. ADG is an adjective. NN is noun, NNP, like again, like plural form, singular form, all these things are taken into account. Was that your doubt? I mean,
Yeah, yeah. Okay,
okay.
I'll just open. Yeah, get it now.
Yeah,
Thanks.
yeah, okay.
Ma'am, can you please give me explain once?
Uh,
What about the repeated words?
what about repeated words? Repeated words where?
Here, no, ma'am. Actually, one more example is in a assignment problem. So in that, repeated words is there.
Repeated, okay. Repeated word as in, let me think of a. So in a sentence, you have the same word being repeated twice, is it?
Yes, ma'am. Actually, is A grade having the single tag, ma'am? Is VB and A
Uh-huh.
is DP and grade is adjective.
Uh-huh. So here the main idea is say any some other sentence is also given, okay? So for each word, you have to start at each word and see
Yes,
how
ma'am.
many possibilities are there, what possible POS tags it can have. Take account of that, then move on to the next one, and same thing you have to do. So irrespective of the number of words, irrespective of whether the words are repeated, that doesn't matter. Just for each word that is there in the sequence, you see what are the number of possible POS tags it can have, and then you simply you count it and you multiply it across all the words. That will give you the solution for this problem.
But in the solution, 4 into 3 into 1 into 1 into 1 into 3, ma'am.
Yeah.
But in the absence of 4 into 3 into 3 is there, ma'am.
So 1 into 1 would be 1 simply. So it is implicit over here. So actually over
That's
here that I
why,
mentioned, so this is a
yes.
solution, right? But 1 into 1 into 1 is simply 1, so we just omit it in the final solution.
So finally only 4 into 3 into 3 only, madam.
Yes, yes, yes. So that is a product. Ultimately, it would be like
For example, in 4 into 4,
Hmm.
so 4 into 4 into 1 into 1 into 1 into 3 is rightly simple as 4 into 1 into 3, ma'am.
So I didn't catch all of your numbers. So if there are any ones, you can omit it. So if there was some other one after it, so say it would be into 1, into 2, into 3, you can omit the 1. You can simply write the
No, ma'am.
numerical.
Actually 4 into 4
Hmm.
and 1 into 1 into 1
Huh.
and 3.
Huh.
And then we simply write as 4 into 1 into 3, ma'am.
So it will be 4 into 4 into 3.
2 times 4, ma'am. 4, 4.
Huh.
And 4 pure stacks.
Yeah. So it would be
That
4.
is 4.
Yeah, so wait, so you're saying, just a second, I'm typing in the chat what you're saying. So this is what you're saying? This is the value of dot?
Yes, ma'am. Yes, ma'am.
Yeah, so simply you can, so after computation, it will be simply 4 into 4 into 3, or you can simply multiply it, okay? So what would be, you can simply multiply the value and whatever you get, that would be the answer.
No, ma'am. I didn't get.
Okay, no problem. Just wait a second. Okay. So,
But as
death
per
comes
question, only one
twice.
code possibly done is there. Right.
So that is, yeah, I was just giving an example.
Okay.
Yeah. So let's modify the sentence a little bit. Okay. Uh, so let's say that it would be not a very coherent sentence, but just to give an example, I would say. So Death Note is a great Amin, and then again say Death Note comes. Okay, that is the entire sentence. Okay. So the final sentence is Death Note is a great an anime Death Note. So there are now 8 words in the sentence. So what would be the solution in this case? So for death, we see what are the possible pure stacks. This is NN, NNS, NNP, and NNPS. We
4.
just so it would be 4. That is the number of possibilities. For note, it's 3. For is, it's 1. For is again 1. For great, it's 1. For anime, it's 3. Then again death would come. So it would be 4 again, and note would come. For that, it would be 3. So now you simply
Yes.
multiply all these numbers.
So 4 into 3 into
1 into 1 into 1 into 3 into 4 into 3.
so we got 4 into 3 into 1 into 3 into 4 into 3, ma'am.
No. So finally it would be if you remove the ones also, it would be 4 into 3 into 3 into 4 into 3. That would be the final answer. Right?
Yes, ma'am.
Yeah. Is it clear now?
So 3 into 3 is repeated now. So simply one time 3. Right, one time 3.
No. No. You have to write. You have to. That would be there. That is just you have to multiply. So here you're simply multiplying only because one doesn't contribute to the addition to the multiplication. We can remove it, but others we need to keep.
Okay, ma'am.
Yeah. Any other doubt, anyone? Is this clear for everyone? Is this question? Okay. All right. Let's discuss the next problem. So here we need to give you have to give the amount of time required, and we have been given certain values. The number of possible hidden states is given. The length of the observed sequence is given. Now we need to answer what is the time. Nobody has answered the question yet. Um, I I think maybe we can discuss the solution, and in case anybody has a doubt, you can ask. So here the answer is A. So how do we get to the answer? So we have been asked to compute this, right? So as you can see in the problem, what it is given to us is we need to find the joint likelihood of the observed sequence O and the hidden state sequence Q. So this is what we need to find. So in order to find this, first we need to find that so 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 here what it is given that there are n possible hidden states and t is the length of the observed sequence, right? So from here, we can find that n to the power t would be the possible hidden state sequences, okay? Q for all for the sequence of length t. So, uh, so, so, um, so at each, so t is the length of the sequence, right? So for each point, there are n possible values that it can take. So that gives us n into n t times. So that is why it is n to the power t. And finally, once I have this, then we simply for each possible such sequence, we simply need to calculate the probability. So that would involve t multiplications. So because of that, the final answer is t into n to the power t. So is this clear? Any doubt on this problem? You can ask, you can unmute yourself and ask, and put in the chat as well. Is this clear? Please explain it again. Okay, sure. Okay, so what we need to compute is we need to compute the joint probability. Okay, so in order to compute the joint probability, first we need to have a count of the all the possible hidden state sequences Q that are there. So we have been given that the t is the length of the observed sequence. Okay, so there are say so x1, x2 to x capital T. Okay, that would be the all. That would be how I can represent this observed sequence. Now for each possible such value. So remember in pure stacking. So in pure stacking, what we would have say. So there was this example which Sir gave in the lectures, right? So it was promise to back the bill. So that was there, right? So here, this is the observed sequence. Okay, and what is the length in this case? So promise to back the bill, right? So there are 5 words. So that is what is T over here. Now what do? We are given n possible. So there are n possible hidden states. So what are the hidden states in pure stacking? They are the pure stacks. Now over here we are not given any explicit like state values. We are given the possible numbers. So for each x1, x2, x capital T, each can take n possible values. So for example, in pure stacking, see the first word was promised, right? So promised can take, say now we know nothing. So it can take any possible pure stack could be assigned to it. So that is what it means. Okay, so it can be a noun, it can be a verb, adjective, anything. Okay, for simplification of the problem, I'm saying that in reality that is not the case. So now what we have, so for each of the possible term in the observed sequence, I have n possibilities. So here the length of the observed sequence is t, so I need to multiply n t times. So n is the number of possibilities for x1, n is the possibilities for x2. Similarly, goes on till x capital T, it also has n possibilities. So we multiply n t times, that gives us n to the power t. Okay, so that is the possible hidden state sequences, all the possible hidden state sequences. Now for each hidden state sequence, I need in order to calculate the probability, I need to do multiplications, which would be of the order of the number of terms that are there in the observed sequence. Okay, so for that we need to do t multiplications. And so so for each of the n to the power t hidden state sequences involves t multiplication. So finally we do a product of these terms. So because of that we get t into n to the power t. Is it clear now? How about others? Could everybody understand this problem?
Yes, ma'am.
Okay. Okay, so this was the last practice problem for today. We still have about half an hour. You can discuss any doubts if you have from the slides. So you can let me know if you all have any doubts.
Can you come to the first question we discussed about the days and weather?
Yes. This one?
That's the one.
This one?
Yes.
So you want me to explain the problem again?
No, in the solution, you are saying the first day is considered to be the start day, P of S3 start.
Hmm.
You showed me, I think, one more slide where you computed the values.
This one?
Yeah.
Yeah, so here, where's your doubt? So should I explain from here? So this was the observation. Yes. So this is the observation sequence for which we need to compute the probability. So how do we do that? So here, this is a normal HMM model. We do not have separate states, and we do not have hidden states and observable states. We have only one state, which is the observable state. Okay, which is like we can see whether the weather is rainy, sunny, or cloudy. Okay, so here we have only one state. So here we would not have any emission probability. All we have are initial probability and transition probability. Okay. So initial probability comes where we need to start from some sequence, right? Not some sequence. We need to start from some state. Okay. And what is the starting state over here? It's S3. Because of that probability of S3 given start. Next is from S3 we transition to S3 again. So the first day was sunny, the second day is again sunny. Okay. So what is the probability of that? What is the probability of transitioning from S3 to S3? It is 0.8. Okay. So that is what these terms are.
Yeah, madam. But actually, the asked a question that
Uh-huh.
asked only seven possible probabilities, right?
Okay,
Seven.
okay. Haha. So they have asked that what is the weather for the next 7 days, given that the first day is state 3, right? So you need to start from t equals to 1. Okay. T is
Yeah,
equals
that
to
still considering it as sunny on the first day, so that satisfies the first sunny day, right?
satisfies the first sunny day. Yes.
So why do we again go for probability of S3 to S3?
This one. This
Yeah,
is
that
the second term. This one, right? So this is like the first day was sunny and the second day is again sunny.
okay. If we consider like that also, we have eight probabilities computed here.
Huh, yes. So you're saying if we can omit this first term that you're saying?
Yes.
Pro-
Or either we can omit the first term. If we consider first itself as a sunny day, we can omit the
then
second
also,
one.
yeah. Yeah. It is given, so there's no ambiguity over here. So it's given that the first day is sunny with probability 1. So all other instances where where the first day is cloudy or rainy would have a probability of 0 automatically. So that also
Yeah,
is.
that value is one, it's not impacting anything.
Yes,
Like it
yes.
would have been something different.
Hmm.
We may have the varied output here actually.
Yeah, correct. Yes.
So yeah, my doubt is that since the day itself is they say the start day and it is sunny,
Mm-hmm.
why do again we consider two more sunny days? Sorry, three more.
Two more only. So see over here it's given sunny, sunny, rainy, rainy. Okay, this is for the 7 days, the next 7 days. So starting from the second day. Okay, whereas the first day is also given to be sunny. So because of that, there's sunny, 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 three sunny. Uh, Okay. So this is from the second day onwards. So this is t is equals to 2, t is equals to 3, t is equals to 4. But whenever you're taking into account any observation sequence, it needs to start from time step 1. Okay, that is the initial condition. Okay, so because of that, you need to have t is equals to 1, it was sunny, then 2, then 3, then 4, like that. Hmm? Did you, is it clear now?
Yes, yes.
Okay. So we'll be continuing the live session. So we have time for half an hour more. So I would request all of you to ask doubts that we can discuss. Anybody has any doubt from the video lectures this week, previous week? So we can take that up. We can discuss from the slides as well. Yes, somebody has raised the hand. Oh, okay. Let's discuss something from the slides then. In meanwhile, you all can ask doubts. You can post in the chat or unmute yourselves and ask. Let's see what we can discuss from here. Hmm, maybe I can talk about the Viterbi algorithm. Many problems today was from based on this concept. So say we have the sentence promise to back the bill. So what is this? This is the observe sequence. Observe sequence consists of words in this case, whereas the hidden states would be the possible tags associated with each of the words. Okay. So when we take the word promised, it could have two possibilities. It could be VBD or VBN. VBD is the past tense form of the word. VBD is the past tense form. VBN is the past participle form. So promise can be both of those things. Okay. And this is my first state. Okay. Next, I have the word to. Two has only one possibility. There's no ambiguity over here. So this is required. So certain tags are there which does not have multiple POS tags, whereas some are there which can have 3 4 possibilities. Okay, that is the most concerning thing, and that is what we are trying to resolve with this Viterbi decoding algorithm. Okay, for example, here we see the word back, right? Back has 4 possibilities. It can take 4 possible tags. The again can be two things. It could be determiner, it could be NNP, and finally bill, it could be verb or noun. So what do we do in the Viterbi decoding algorithm? We simply try to find which is the best possible tag sequence given this information. Okay, Otherwise, if we try to enumerate all the possibilities, so one of the questions today was what are the different possible, if we enumerate all the possible tag sequences, how many would be the number in this case? It would be 2 into 1 into 4 into 2 into 2, right? So that is a large number, and it would become larger and larger. It would be exponentially large as we increase the number of words in the sequence, and also as the possibilities or the number of pure tags associated with a word increases. So in that case, that would be very difficult to compute. So because of that, Viterbi algorithm was introduced, which is a dynamic programming mechanism where at each step, okay, we're at each step, say we are at this step, we find what is the best possible path of coming to this possible state. So which is, so say over here, we are over here at the word the. So the can have two possible POS tags. It can be DT or NNP. So what we do in Viterbi is that, say for the tag NNP, we ask what is the best possible state it could have come from. So it could have come via this, via this, via this, via this. So that is what we compute, and we keep it ready for each of the states. Okay. So so that is the main idea, and that helps us eliminate many redundant computations that we are doing. So because of that, via dynamic programming approach, we can easily, in a very efficient manner, we can compute the POS tags. So that is the main crux of Viterbi algorithm. Vikash is saying that I think you can, but I'm not exactly. I do not know about the eligibility criteria. What maybe some of the students who are present in the chat can answer to Vikash. Vikash is asking that he is attending this the first time today, so he hasn't submitted any assignments. So can he still would be eligible to giving the exam? Is that your question? I think. So I think somebody from the chat, somebody from the students can answer. You can, or you can drop a mail to the NPTEL team. I think SK is saying, so I think you need to submit 8, so there would be 12 assignments corresponding to 12 weeks. You need to assignment 8 of them in order to be eligible. Okay. Uh, okay, I think Vikash, many of the students have posted. So I think now I think you know what is the eligibility criteria. Um, so does any of the students have any other doubts?
Please explain the maximum entropy model, ma'am.
Maximum entropy model. Okay. So this HM based POS tagging that we are doing, it was a generative model. So what happens in generative model is that we have the hidden states, and from the hidden states we generate the data. Okay. Uh, So this has some concerns. First is, what about unknown words? What about words we never encountered in the data? So we don't have, so for such words we won't be able to compute the POS tag. Okay. One possible solution that has been mentioned is that you can use morphological cues, but in HMS POS tagging, we do not have any way to incorporate these features. So if you want to incorporate morphological cues, say if a word has, say for example, the word is watched. Okay, here watched is, it has an ed at the end. So here the suffix could be an indicator that this word is a verb. Okay, but we don't have any such mechanism to incorporate feature based aspects into the Markov model. Okay, similarly over here also, and what we are doing is we are only taking into a context only the previous word when we are doing HMM modeling. So that was one of our assumptions, right? So we only taking into account the previous one. Now that is very limited context. Why? Because you can clearly see over here, so there are two sentences: is clearly marked and he clearly marked. Here then the first sentence, marked is a past participle form of the verb, whereas in the second word, marked is the past tense. So this is a past tense verb. Okay, so one thing is that we can increase the 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 order of the Markov model. We can take, maybe we were using currently bigrams. We can take trigrams and uh, like four-gram models, but those also have concerns because they have like, so for first thing is that computation would increase, and also with higher order n-gram models we have the concerns of sparseness. So to avoid these problems, we have a maximum entropy model. Maximum entropy model is a discriminative model. So here we can directly compute the probability of y given x, so probability of the tag given the word. Whereas in HMM, I hope you remember, we started with the noisy channel model, and from that we use the Bayes rule, and we're indirectly computing. Okay, we are not directly computing the posterior probability. Whereas in maximum entropy model, we can directly do that. So this allows, so in maximum entropy model we can incorporate different features. So we can incorporate whether like whether the current word that we're processing is the next word too, or whether the last five words is a preposition. So we can design certain binary features, and we can use that in maximum entropy modeling. So that is a flexibility that maximum entropy model gives us. So I think there would be an example we can, so for example, see over here. So here we take into account, so when we're designing the features, we take into account both x and y. Okay, so x would be the context and y would be the tab. Okay, so as we can see, so if W is the word for which we are currently processing, what we can do is we take different features. So we see that is the word capitalized and is Y NNP. Okay, so usually NNP is proper noun. Okay, so usually we observe that proper nouns, the first letter would be capitalized. Proper nouns would be a name of a person or a city or a place. So those usually start with a capital letter. So this could be a very good indicator of indicator or a feature that we can use in maximum entropy model. So if this is satisfied, so as you can see, this is a binary feature. It assigns either a value of 1 or 0. Okay, like this we can assign, we can create different features. Say one feature could be, does the word end in ed? If the word ends in ed, and then we can say, okay, it's a verb. It could be a verb past tense or verb participle, or you can say, does is the previous word the? Usually usually nouns follow the, right? Usually determiners are followed by a noun. So uh, say the dog is barking, so over here the usually follows, and the is usually followed by a noun. So all these features you can incorporate, and this couldn't be done in the HMM model, but we can do this in maximum entropy models, and so that is where this is useful. So there are other examples which Sir has given over here. So you can not only in pure stacking, you can use it in other sequence labeling tasks. Another very prominent sequence labeling task is that of named entity recognition. Okay, so here say we are trying to find.
Ma'am.
Yes.
Yeah, this in this slide the example features is there now.
Hmm.
In the first example, the location in Arcadia, based
Hmm.
on that they consider the features.
Yes.
In the second example, the
Hmm.
Y is the location.
Hmm.
In In the first example, they clearly say y is equal to location, and they consider the future in is capitalized word. Can you explain this that example, ma'am,
Yes,
based on the features?
yes. So here, if you see the first word, so this is W, okay? In Arcadia is the context that is given to you, okay? Here W is Arcadia, W minus 1 is the word preceding Arcadia, that is in, okay? And location is the tag, which is the tag or the class in this case. So the class is location, Arcadia is a location. So that is what it means. Y is equals to location. Y minus 1 is the previous word in. Yes, it is. It is in Arcadia. And is capitalized W. What is W? W is Arcadia. Is it capitalized? Yes, it starts with a capital A. So that is what it means. The three of the features are satisfied. So for this, this feature
The
would be.
second example is the same example, ma'am, but the future is different, ma'am.
So second example would be, second example is corresponding to this one in cubic. So here we see that the class is that of location, whereas if we see has accented Latin character. So here we see there's this E. This is an accented Latin character. So that is an indicator. So these are just like based on the data that we are manually trying to design features. So the feature 2 that is there, it would be 1 for this one, so it would be satisfied for this second example, but for the first example it would be false. So it is not a very good identifier of a named entity. Does that clear your doubt?
Yes, ma'am. Okay.
Okay. Mm, any other doubt? um, could you please explain the last question with one example? Yes. Okay. I hope you can see this, right? So in the last example, what we are given is, we were given that the number of possible hidden states is n, and t is the length of the observed sequence. Okay, so so we'll discuss in the context of POS tagging because that is the one we are most familiar with. So here, what would be the observed sequence? It is the sequence of words that we have promised to back the bill. Okay. And what is capital T? Capital T is the length of it. So there are 5 words. So capital T in this case would be 5. Okay. Now, what is given is here we are given that promise can take either of VBN or VBD, but that is not mentioned in the problem. There in the problem it is mentioned that it could take any of n possible hidden states. Okay. So and what are the hidden states in POS tagging? Those are the POS tags, which are VBN, VBD2, all these things, all the trellis that you can see, all the values that you can see in the trellis, all of these are hidden states. Okay. But here we are not given explicitly that what are the concrete set of pure stacks or concrete set of uh, um, hidden states for each of the word in the observed sequence. Here we are given a generalized value that n is the overall possible hidden states. So for promised, in that case, there would be n possibilities, n possible pure stacks. Okay. Similarly, for 2, there would be n possible hidden states. Similarly, for back, there would be n possible hidden states. Now, in overall, we have 5 words. It would be it would be n into n into n into n into n. So in this case, it would be n to the power 5. Whereas in the problem, there were n words in the observed sequence. So in the problem, it was n to the power t. Okay, and what is this n to the power t? This is any possible path, right? All the possible feasible pure stack sequences that we can obtain. Okay, that would be n to the power t. Now for each, so if I take any one of the sequence, for that I need to further compute the probabilities, right? And What is that equal to? That is of the order of the length of the sequence. So I need to traverse each of the words and I need to calculate the probability. So I need to do overall ordered t multiplications for each of the n to the power t sequences, state sequences. So finally we have t into n to the power t. So that is the
For
order.
this, it
Yes.
means for this example, it
Hmm.
will be 5 into 10, 11 raised to 5.
11 raised to 5 as in 11 you're getting for the number of tabs you're saying?
Number of years times.
Yes. 11 raised to the power 5 into 5.
Is it right?
Yeah. 11 raised to the power 5 into 5. Finally also you need to multiply the 5 as well. Right?
Yes. 5 into 11 raised to 5.
Yes, yes.
Thank you, ma'am.
Is it clear? So SS Barfe had asked. Is it clear now?
Yes, ma'am.
Okay, you had only asked. Okay, okay. Okay. Any other doubts? We can take up topics from the previous lectures also, previous week's lectures as well.
Ma'am,
Yes.
in the third week assignment, the question number 9, we got 4.99966 into 10 power minus 8 9. But the assignment is wrong answer.
Assignment, okay. In
We got a 4.966 into 10 power minus 8 9.
okay. This is
But
one
in the
of the
NPT,
acha acha detail. Okay. For that, I think you need to so assignments and all. We don't design, like we don't create them. So NPTEL team would be the best you can contact. Saying there's a
okay,
mismatch here for mismatch and solution.
okay. Okay. Your email is there, ma'am, for
Uh,
contacting NPTEL team.
NPTEL. I also have to search. Just a second. It will be there in the SWAM website is there, no?
Okay,
So it
yes,
would
ma'am.
be there.
Okay, thank you.
Madam,
Yes.
what is perplexity?
Perplexity is a notion that allows you to understand how good or bad a language model is. Okay. So let's look at the slides. Just a second. Huh, okay. So yeah, I hope my screen is visible. So we'll first understand the intuition behind perplexity. Say I'm given this sentence, I always order pizza with cheese and dash. So if I ask you to fill in some possible word over here, so what would you say? Maybe you'll say pepperoni or maybe paneer or something like that you would say, right? Whereas if you say something weird like say coconut or orange, those are not valid pizza toppings, right? So those won't come over here. So that is what is the intuition that a language model should be predicting a more probable word over here. Probable word is so words that go in with this context. Okay. So that is the idea. Now, what does perplexity do is that say, so perplexity would mean how perplexed the model is. So here when the model is filling in the gaps, so when the model is performing fill in the blanks, how many possibilities it has. The more the number of possibilities it has, the more it would be confused. But for a better language model, it would be much more confident about which are the valid options over here. So say if there's a language model who considers all these, say, pepperoni, cheese, and orange, and all these things to be probable, very probable candidates to fill in the blank. That is a bad language model, because it is not able to distinguish between valid and invalid options and getting perplexed, okay, by the higher number of possibilities. Okay. So, so say for example over here, so this is a nice example. So we have n random digits in a sentence and need to compute the perplexity. The formulation of perplexity is this. So this we need to take the first need to compute the probability of the test data, then need to inverse it, and then we need to normalize by the number of words. Okay. So in this case, when we first calculate the probability of the data, so there are n digits, each has a probability of 1 by 10. So 1 by 10 to the power n would be probability of the test data. Okay. Now when we invert it and finally obtain the perplexity, it gives us the value of 10. What does it mean? So say I'm asking the model to predict the next digit. It has 10 possible options to choose from. So it would be perplexed at which of the 10 numbers is a valid candidate for the uh, next digit. So that is what it means. So higher the perplexity, worse the language model is, because it's perplexed. Because it is perplexed, confused among more number of options. The better the language model, it would have a lower perplexity score. Okay.
But
Hmm.
but my question is, if our data is unlabeled, in that case, it may impact the perplexity of our language model, right?
Data is unlabeled as in.
Unlabeled, that means, suppose pizza word is not occurring in my corpus, and if I am giving the query in which this pizza word is present, so it may give the wrong answer, right?
Okay, okay. It can give, so unknown words are a issue for language models. So whether it be the engram-based language models or the current language models that are there, so it would be a concern. But one thing I would like to say that, so this example that I gave, this is just for intuition. Ultimately, it would boil down to, as you're saying, if pizza was not there, you would not have a probability corresponding to it. So if you don't have a probability value corresponding to a word, ultimately the entire perplexity would be zero. Okay. No, sorry, not the perplexity. The probability of the test data would be zero. And for that, we won't be able to compute perplexity, because that would involve taking inverse of a zero value.
Okay. Thank you, ma'am.
Okay. Sita Lakshmi has raised her hand. Yes. Any other doubt? Sita Lakshmi had raised her hand. So if you have any doubt, you can ask.
No, ma'am, I don't have any doubt, ma'am. A mistake.
Okay, okay, no problem. So we still have some time. We still have 2 minutes. You can still ask some doubts if you have. So I hope you all have gone through the week fours. Is there any lemmatizer for Marathi language? Um, I don't think so there is, but there's a morphological analyzer available for Marathi language. So maybe you can use that. So it won't, they are not exactly like, they are not one-on-one correspondence, but on morphological analysis also you obtain the lemma, right? So you can use that.
Madam,
Yes.
can I find out the number of keywords from a Marathi corpus?
Number of keywords. So again, keyword, what do you mean by keywords?
Keywords means in Marathi there are some words like ahe,
Huh.
astat,
Hmm.
just like in our English language, is, are.
Hmm.
So
Okay.
can we remove those keywords from a Marathi corpus?
I think you can. So those would be function words, right? So like you're saying ahe and all those words would be occurring with a very high frequency. So if you can find out what are the most high, so you can use Zipf's law over here and find what are the most frequent words in the corpus. So the corpus would have say 10,000 words. Among them, take the top say 50 most frequent words. You'll find ahe and all these words over there. So from that you can get, so these would be the stop words. So you can filter them out and then you can walk. Is was that your doubt?
Okay, thank you, ma'am.
Yeah, okay. So Shubha is asking, yes, the recording would be available. So there's a sheet posted in the portal. From there you can access all the recordings. Okay, thank you everyone for joining today's session. We'll conclude today's session. Thank you for joining.